I'm audible and I hope my screen is visible, right? Okay. Yeah. So let's start. So so mm, this is tutorial 8 of the course Advanced Linear Algebra, uh, which is NPTEL code is, and today is 14th March. Yeah. So so in today's as like to the previous tutorials, in today's tutorial also I will try to solve some problems, and during that problem, when I'm trying to solve those problems, whatever the theorem is needed, I will mention that. Otherwise, I'll not mention. But today only I mention only three some already known fact which I already discussed. Let V be a finite dimensional vector space. V be a finite dimensional vector space over a field F, and which is most of the time either real numbers or complex number. Let T from V to V be a linear operator. Then we know, okay, then we don't need, then we know if, then we say T is diagonalizable if there exists an basis of V consisting eigenvalues of consisting eigenvectors of T, right? So this is so T will be linear, T will be diagonalizable if there exists an um, basis of V consisting eigenvectors of T. Okay, so this is called diagonalizable, and this fact is, and as we know, if we consider let beta be a fixed basis, order basis, if I fixed order basis of V, then good evening. Then if beta be a fixed order basis of V, then the matrix representation of T, uh, then 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 T is diagonalizable. Then T is diagonalizable if there exists an invertible n by n square matrix, invertible square matrix P, such that such that the matrix representation of T with respect to the order basis B and P inverse P is a diagonal matrix. Okay. So this is what it is, diagonalizable in both the sense. Whenever I am considering it as a linear operator on the vector space V, then it is diagonalizable if V has a basis consisting all the basis consisting eigenvectors for of T, then it is diagonalizable, and this fact is equivalent to the, if you consider an order basis beta of V, and if you consider its matrix representation with respect to that order basis beta, then there must exist an invertible square matrix P such that P inverse T B P is a diagonal matrix. That means all the entries except the diagonal will be 0. Okay. So 0 matrix itself is a diagonal matrix. Okay. So why I'm saying diagonalized matrix? So till now, the most important theorem till now what we have discussed or encountered, that's the diagonalizable, a linear operator always on a finite dimensional vector space, linear operator T on a finite dimensional vector space V is said to be diagonalizable, not said to be, is diagonalizable if and only if, so this is if and only if its minimal polynomial is completely factorized into distinct linear factors. What does this means? Uh, what does this means? This means that P will be, suppose P is the minimal polynomial. Let P be the, so that is, let P be the minimal polynomial, or if P be the minimal polynomial, if P is the minimal polynomial of T, and C1 all the way Ck are a distinct eigenvalue of T, then P of X, that must be X minus C1, X minus C2 all the way X minus Ck. So, and so what I just want, what I'm trying to say is that there should not be any power as well. Power is one always. That means there will not be something like 2, 3. If the minimal polynomial has something like this, that x minus ck to the power 2, or some repeated power, I mean some power is there, some power which is greater than 1. So in that case, that is not diagonalizable. Okay, this is one of the already known fact. We already used this fact, but you can remember. I just wanted to mention these facts. There is a reason, because today I will be using something called Jordan canonical form. So that's why I'm trying to use this, because in the whole one of the main purpose of the linear algebra, basic linear algebra, was like that you have to reach up to Jordan canonical form, and Jordan canonical form is something like that the simplest form of a matrix can attain. Okay, the simplest form of a linear operator is the Jordan canonical form. That actually something like that. That is a matrix which has more zeros and less non-zero entries, and those non-zero entries are 1. So basically, Jordan canonical form of a matrix is the identification of that matrix by only 0 and 1, which where the number of 0 is maximized, something like that. Okay, so I will go to that Jordan canonical form. But diagonal matrix is diagonalizable matrix or linear operator for which the minimal polynomial is this. And recall that minimal polynomial is a P is the minimal polynomial is the smallest degree monic polynomial P, such that P of T actually 0. This is the minimal polynomial. This is the definition of the minimal polynomial. Okay. So I will not go that, and you have characteristic polynomial, and whenever the minimal polynomial is look like this way, then characteristic polynomial will be something like x minus c1 whole to the power d1 all the way x minus ck whole to the power dk. This is characteristics polynomial. So in characteristics polynomial d1, d2, dk, their sum will be automatically n, because characteristics polynomial is always of degree n if V is the vector space of dimension n. So here V dimension of V is actually n. This is dimension of V actually always n. Okay, and minimal polynomial and characteristics polynomial should always have the same root, basically same root. They will have always same root. Okay, so this is what it is. So now, if we have a, so diagonalizable is this. Another fact of diagonalizable is that if T is diagonalizable, so this is something like that. Another fact I am saying T is which I have discussed in the last class. Even if you have any doubt, you can ask here. I will try to explain once again. And in fact, apart from this doubt, if you have any other doubt regarding this course content or assignment, you can ask. I'll try to explain those. So if T is diagonalizable, if and only there exists a distinct scalar or element in field Ck in the field such that T is equals to summation of Ci Ei I equals to 1 to K. So this Ei with where E1 all the way Ek satisfies the following property. What are the following property? First of all, Ei's are projection for all I equals to 1 to K. Second is that they are orthogonal, basically something like that. Ei is equals to 0 if I not equals to j, and their range will form okay, so this is what it is mean by this is what it is. This is equivalent to that V is actually W1 direct sum all the way WK, where Wi actually the range of some space. Ei, here is the Ei are operator on V. So these are the simplest operator. They are projections basically. So this is what it is, one of the criteria. Even if you have any doubt with this criteria, you can ask, or not able to understand any terminology, you can ask. I'll try to explain. And if you have any other problem, you can still ask from there. So let's go back to the. So okay, let me write the Jordan canonical form basically. Okay. So for that, I'll just first write Jordan canonical form, and then I'll go back to the problems. So Jordan canonical form of a matrix. Right now, of a matrix, because every linear operator has a matrix representation, and that matrix representation is actually equivalent. That matrix representation is similar actually to the any uh, whatever the Jordan canonical form, that will be similar. So before going to the Jordan canonical form, I just wanted to mention some facts. First of all, let T from V to V be a linear operator on a finite dimensional vector space V. Then, if characteristics polynomial fx is equals to x minus c1 whole to the power d1 all the way x minus ck whole to the power dk. Let, I'm assuming, so here c1, c2, ck are distinct eigenvalues of t. Second is that minimal polynomial px that is equals to x minus c1 to the power m1 all the way x minus ck mk. Okay, where mi is always less than equals to di. Di is called algebraic multiplicity of the eigenvalue ci. And let, this is one of the important fact. This is where, but here is the one important fact. Geometric multiplicity of the eigenvalue ci is equals to the dimension of kernel of T minus Ci identity. Basically, the dimension of the eigenspace, number of eigenvectors, distinct independent eigenvectors corresponding to Ci, number of independent eigenvectors corresponding to Ci. So this is geometric multiplicity, which in algebraic multiplicity is denoted by AP, and geometric multiplicity is denoted by GP, and in general, GP is actually less than equals to AP. That I have discussed a little bit in the previous class. That whenever you have v number of eigenvectors, I mean geometry. So let me connect this. Algebraic multiplicity is actually the power of x minus ci in the characteristic polynomial, and geometric multiplicity is not the power of x minus ci in minimal polynomial. That is not. Geometric multiplicity is actually the power of geometric multiplicity is actually the number of independent eigenvectors in the corresponding eigenspace, or the dimension of the eigenspace corresponding to the eigenvalue ci. Now geometric multiplicity is always, sorry, this is not geometric algebra, AMGM, sorry, AMGM. GM is always less than equals to AM. This is what it is, and that I will not discuss. This is one of the facts. Now another fact I just wanted to mention here, which actually characterizes, in this case, T is diagonalizable if and only if AM is equals to GM. So why I have written in this case? Because here we have assumed the characteristic polynomial of the linear operator is this, right? And but characteristic polynomial is not always should be factored like this way. If it is not factored like this way, then there is no terms of diagonalizability. Okay? But still there is making sense of Jordan canonical form and all these things. But if it is factored like this way, then we can talk about anything, whatever I have talked till from here to here. Okay. These things only be talked about whenever characteristic polynomial is completely factorized into linear factors. This is completely factorized into linear factors, but need not be distinct. Why it is need not be distinct? Because x minus c1 to the power d1 is there. That means if d1 is greater than 1, so d1 is greater than 1, then that means there is a repetition of x minus c1. That's why it is not distinct. Okay. But factors in linear factors. Characteristic polynomial need not be factor always look like this way. Okay. That can happen that there will be some polynomial, some factor which is of degree 2, degree 3. That can happen. And I will encounter those things also. But let me first write Jordan canonical form. Okay. So this, but whenever we have this type of things, there. Okay. So the Jordan canonical form, I'll explain it later. So whenever you have this type of things, so the question is whenever the characteristic polynomial will be factored into linear factors. Whenever the field, underlying field, is considered as the algebraically closed field. In particular, if we consider V is a vector space over the complex field, then always the characteristic polynomial will be factored into linear factors. Okay, these are linear factors. Okay, x minus c1, x minus c2. Whenever it is of degree 2, that's no longer linear factors. Okay, so now let's come back to a new problem, and after that I will, whenever Jordan canonical form is explicitly needed, I'll come back to that point. Okay, so here is a problem. So what this problem says? This problem says let T be a linear operator on R3 such that the matrix representation of T with respect to the standard ordered basis A is A equals to this. Let T1 is equals to T minus 2i, T2 is equals to 2 minus 3 to 2i square, T3 is equals to T minus I, T4 is equals to T minus I square. W1, W2, W3, W4 be the respective null space such that R4 is actually W1 plus W2 plus W3 plus W4. Let P be the minimal polynomial of T, and which of the following statement is or are correct. So basically we have to find the minimal polynomial of T. Okay. So how to find the minimal polynomial? So first let me find the characteristic polynomial. Okay. So but here I have to use the primary decomposition theorem. So let me mention that theorem first. Then I'll go to the program. So primary decomposition theorem, what it says, this is very important theorem, primary decomposition theorem. So always we may not have the situation that the linear operator is always diagonalizable. Primary decomposition theorem is something when we can say what is the best one can get something like that. Primary decomposition theorem or Cannonical form is something like that. What the best one can get for a linear operator T, which is not necessarily diagonalizable. If an operator is diagonalizable, that means that is similar to a diagonal matrix, right? But if it is not diagonalizable, then what the best one can get for a linear operator T, that started from the primary decomposition theorem. Primary what it says, let T from V to B be a linear operator on a finite dimensional vector space V, and let P be the minimal polynomial of T. Let P is equals to Px is equals to P1x to the power R1, P2x to the power R2, and Pkx to the power Rk, where P1, P2, Pk are distinct monic irreducible polynomials, where P1, P2, Pk are distinct monic irreducible polynomials, and with the fact that some facts the monic polynomials and R1 Ri's are some positive Ri's are positive integer. Let Wi is equals to range of Pi to the power Ri. Then what primary decomposition theorem says that Wi's are invariant subspace of T, where TWI is actually, that means TWI is actually subset of WI for all I equals to 1 to k. Second thing is that the vector space V actually direct sum of W1, W2 all the way WK. And third fact, if we restrict that each DWI is actually invariant under T, right? So we can restrict T to WI. Okay, TWI is a linear operator on the subspace Wi for whose minimal polynomial is minimal polynomial is Pi t to the power or Pi to the power Ri. Okay, so what I have said, this is very interesting, and actually important point is that you have to understand what this is trying to say. We can solve many problems using these statements, but you have to understand what it is trying to say. V is a finite dimensional vector space, T is a linear operator on the vector space V, and P be the minimal polynomial. And let's take, you can decompose the P is a polynomial, so you can decompose into its irreducible polynomials. Okay, so here each Pi are irreducible. It is said that each Pi is irreducible. That does not guarantee that Pi x is necessarily x minus Cy. This is not. This can be this form, but also this can be something like that x square plus x plus 1, because this is not decomposable. This is an irreducible polynomial. X square plus x plus 1, this is an irreducible polynomial. You can't break it into two product of two polynomial where each of them are polynomial over. No, this is irreducible over real number, but in complex number it is completely reducible. Okay, because what are the two roots of this? This is a 2-degree polynomial. What are the two roots of this polynomial? That's omega and omega square. That is the square root of cubic root of unity. Okay, so then x can be written as x minus omega square, where omega is actually cubic root of unity. But if we consider it is a polynomial over real field, then this omega and omega square are no longer element in the real numbers. So that's why in real number, this polynomial is actually irreducible, but over complex number, this is not irreducible. Okay. So that is what I wanted to mean, that entries can be, these PIs can be x minus Ci like this form also. But this can be also 2-degree polynomial also. Okay. There is no guarantee that there will be 1-degree polynomial. If the field is complex number, then it is always 1-degree polynomial. There is no guarantee. That's guaranteed, because if the field is complex number, then that is algebraically closed field. Then any irreducible, I mean, there is only irreducible polynomials are linear polynomials. This is what it is. So now if P1, P2, Pk are all distinct, okay, they has to be all distinct. Now if you have P1, P2, Pk, and these are the distinct irreducible monic polynomial, and Ri are the sum, their powers are positive, that means they appears or not appears. If we consider Wi actually the range of the polynomial Pi, range of the operator Pi, P to the power Ri, then basically you have this, importantly, V is actually direct sum of W and W to Wk. Here each of W is invariant, and direct sum means intersection W1 intersection W2 is W1 intersection, each Wi is actually intersection with W1 all the way plus Wi minus 1 plus Wi plus 1 plus Wk. This is 0. This is 0. Okay, trivial space. This is what it is I mean by orthogonal. Okay. And if you restrict, now as W is invariant, as W is invariant, T will map elements in W to the elements in Wi. Now if you restrict T to this Wi, then what I will have? I will have a linear operator on Wi. Now this linear operator should have a minimal polynomial, and that minimal polynomial is exactly Pi to the power Ri. Okay, let's come back to the problem. I have discussed lots of theorem today. So this is a problem. So what it says, let T be a linear operator on R3, so either the matrix representation of T with respect to the standard order basis, A is look like this way. So A is actually the matrix 3, 1, minus 1, 2, 2, minus 1, 2, 2, 0. T1 is equals to T minus. So let's find the characteristics polynomial. Okay, that then minimal polynomial. So what we'll get? Let determinant of A minus xi, what it will be? It will be equals to 3 minus x, 1 minus 1, 2, 2 minus x, minus 1, 2, 2 minus x. This is what it is. So this is determinant I am talking about. So this will be this. So let me expand this. This is something we have to work out. 3 minus 2x, 2 minus x into x minus, and the next is minus minus plus 2, minus 1 into minus 2x minus minus plus 2, and minus 1. This will be 4 minus 2 into 2 minus x. So this will be 3 minus x square minus 2x plus 2 minus 2, if I take 2 common, minus 2 common, then it will be x minus 1, minus, if I take, so this will be 1, 4 minus 4 plus 2x, so this will be 3 minus x plus 2x minus 1, so this is 4 as well, 4, 2x, 2x, so 2x, 2x cancel out, minus 2x, so this will be like 2x minus 2 minus 2x, 2x cancel minus 2. I don't know whether I'm doing correctly or not. Just a minute. So this is equals to this is equals to 3 minus x square minus 2x plus 2, let me 3, and minus 2. So it will be like, okay, let's do the calculation. 3x square minus 6x plus 6 minus x cube plus 2x square minus 2x minus 2, so it will be equals to minus, if I take common, x cube plus 3 5 minus 5x square and minus 6x minus 2x plus 8x plus 4. Yeah, I hope I'm correct. So I will write x equals to 1 is root. X equals to, if you replace x equals to 1, so what it will happen? 1 minus 1, 5. 1 minus 5 plus 8 plus 4. There is some mistake I think I made. This will be minus. So then it will be like, if you replace x equals to 1, 1 minus 5 plus 8 minus 4. So it's 0. So that means x equals to x minus 1 is a root. So this is like x square, x cube minus x square. So we need to adjust 4x minus 4x square plus 4x. So we need 4 more, 4x minus 4. So this is actually minus x square minus 4x plus 4 whole into x minus 1. So this is equals to minus x minus 1 into x square minus 2 whole square. So the characteristic polynomial is x minus 2 square x minus 1. So lambda equals to 2 and 1 are eigenvalue for the given matrix, eigenvalue of the given matrix here. Now let's see corresponding to a equals to 2y. So a was, I'm writing 3 1 1 minus 1 2 2 minus 1 2 2 0. I think I have written correctly. Yeah, 3 2 minus 1. This one minus 2 times identity 2 0 0 0 2 0 0 0 2. So this will be like 1. Okay, 1 1 minus 1. So 2 0 minus 1 2 2 minus 2. So if you look at carefully, this first and the last are same. Okay, the two multiple. Okay, so I want to find a minus 2y whole into x1 x2 x3 is equals to 0. Then what will happen, right? So basically, if we do this thing where x1 x2 x3 is equals to 0 0 0. So first and last are says same. So basically x1 plus x2 minus x3 is equals to 0, and another is 2x1 minus x3 is equals to 0. So what we got, x1 is equals to x3 by 2. Okay. Okay. So yeah, this is x1 equals to x3 by 2. So if I replace x1 is equals to this value, then what will be x3 x2 is equals to x3 minus x1, which is equals to x3 minus 1 by 2 x3, which is equals to 1 by 2 x3. So what we got, if we take x3 is equals to 1, then x1 is equals to half and x2 is equals to half. This is, so this says half, so this says half 1 transpose is only eigenvector. I mean, there is no eigenvector, no other eigenvector which is linearly independent to this. Is only eigen. So basically, this is not only eigenvector. The terminology is that there is only one linearly independent eigenvector, that is scalar multiple of this, non-zero scalar multiple of this. So half 1 transpose is the eigenvector of t. Okay, eigenvector of t corresponding to the eigenvalue t, corresponding to the eigenvalue x is equals to lambda is equals to 2. Now let me come to this problem. So this is all. This will be help you to solve the problem. So if you look at carefully, what are the characteristics polynomial? X minus 2 square, x minus 1, right? So what are the possibilities of minimal polynomial? Minimal polynomial should have the same factor will be there. So the minimal polynomial will be either x minus 1, x minus 2. This is the two possibility. possible way of minimal polynomial. So let me write it little more carefully. Characteristics polynomial is x minus 2 square, x minus 1 1. Okay. So possible. So these are the possible minimal polynomial. Choice of minimal polynomial. What are the possible choice of minimal polynomial? This and this. Why this is? Because characteristic polynomial and minimal polynomial should have same factor. They should have same factor. So these are the two choices. But look at carefully. If we have this first option, that x minus 2, x minus 1, these are the type of reasoning you need to do to find the Jordan canonical form when we will be discussing those. So if this is the case, x minus 2, x minus 1, then this is minimal polynomial is actually something like that. It's factored into distinct linear factors, right? So that means that the linear operator will be diagonalizable. So if it is diagonalizable, then the algebraic multiplicity will be equal to the geometric multiplicity. But here, for lambda equals to 2, algebraic multiplicity is actually 2. That is the appearance of x minus 2 in the characteristic polynomial. And geometric multiplicity is actually 1. That is the number of distinct eigenvalues, the dimension of the eigenspace corresponding to that particular eigenvalue. So that means algebraic multiplicity is not equal to geometric multiplicity. But if it is diagonalizable, then the algebraic multiplicity has to be equal to geometric multiplicity, because that's what I have mentioned in somewhere in early. Where is that? Algebraic multiplicity has to be equal to geometric multiplicity. This is if and only. Diagonalizable if and only. That says algebraic multiplicity for lambda equals to 2 is not equals to geometric multiplicity for lambda equals to 2, or of lambda equals to 2, of lambda equals to 2. That says T is not diagonalizable. Then the minimal polynomial is x minus 2 square, x minus 1. I hope it is clear, because these are the very interesting and important reasoning how to do. So the minimal, so only choice left is this one. So this is not the possible choice. This is not possible choice. Why this is not possible choice? Because T is not diagonalizable. Why T is not diagonalizable? Because corresponding to the eigenvalue lambda equals to 2, we got only one distinct or linearly independent eigenvector. This is what it is. So this is the minimal polynomial. So once this is the minimal polynomial, so what the primary decomposition theorem says? Primary decomposition theorem says if W1 is equals to, suppose this is the primary decomposition theorem. Okay, let W1 is equals to range or kernel. Sorry, I think that has to be kernel range. Just a minute. Kernel. This is what it is. W is the null space of Pi minus T. Yeah. Kernel of this operator. So if W is actually the kernel of the operator, kernel of P minus 2 I square and W2 is equals to kernel of P minus identity, then primary decomposition theorem says primary decomposition theorem says that W1 and W2 are invariant subspace for T, and V is actually direct sum W1 plus W2, and if we restrict to TW1, the minimal polynomial for this operator, T restriction is x minus 2 square, and if you restrict t to the w2, then the minimal polynomial is x minus 1. Note that here W2 actually the eigenspace corresponding to the linear eigenvalue 1, but here W1 is not the eigenspace corresponding to the eigenvalue 2. It is not the eigenspace. Okay, it's t minus 2y square, eigenspace of kernel of t minus 2y square, and which actually turns out to be a two-dimensional space. This is very interesting that the kernel of t minus 2y is actually one-dimensional, but kernel of t minus 2y square is actually two-dimensional, and which is actually the filling the left part for the, I mean, suppose, so here is the, what I just wanted to say here is that suppose you have the operator t minus 2y or a minus 2y. So in this case, if we write x equals to 0, then the dimension of this space is actually 1, that half 1, right, that one. But if an element is belong to here, then 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 this space, if you look at carefully, this space, this, if an element x is in the here, so x automatically will be here. So that means this first space is actually contained in there, but the second space may contains more element than the first space. Basically, kernel of t minus 2y actually contained in the kernel of t minus 2y square. Okay, but here is the, I mean, basically fact is that kernel of t minus 2y square, this is something check, you can check for this. T minus square, this is subspace of kernel of t minus 2y square, and which is actually same with kernel of t minus 2y whole cube, and whatever degree you may choose, that does not matter. This is interesting, you can check for 2 3. This is no relation with your fact right now, but this is what it is, very interesting and motivating part from linear algebra, which will go to the further functional analysis or operator theory portion. So this kernel containment will hold, but there will be some point where it will be start to becoming equal, and it will be equal in the next all the cases. That means this is here at dot dot I just wanted. So the kernel of t minus 2y3, that is also same. Kernel of t minus 2y4, that is has to be same. Kernel of t minus 2y to the power n, that is also has to be same for all n greater than equals to 2. So okay, whatever is, this is not needed for our purposes, but t is not diagonalizable. So let's get back to the options. So minimal polynomial is this, that is correct. Minimal polynomial is not this, that's correct. And the here, okay, so here I have to use those terminology. 2 minus ti w2a and w2 w3. This is what it is. This is not. So I have to change those terminology a little bit, because I have written according to mine. This is w2 and this is w3. This is w2 w3. This is w2 direct sum w3. This is w2. This is w3. Okay, so this will solve the first questions. Okay, this is a little lengthy, but this I am trying to actually trying to explain the things which may help you to solve this problem. So is it clear, or you have any doubt, you can ask, or anything you need not understood properly, you can ask. Is it clear? Okay. If it is not clear to anyone, you can ask. I will try to explain, even if I have to go little further. Okay, just a minute. This problem may have some problem. So this is what is another problem. So this is, I think it may be Jordan-Cannonical form. Jordan-Cannonical form. So let's go to the first Jordan-Cannonical form, and then I'll come back to this. So now let's come to the Jordan-Cannonical form. So I'll not explain how the Jordan-Cannonical form comes, but I'll explain some facts or some rules, something like that. Those rules are based on very strong theories, strong, I mean, linear algebra, but I'll be only briefing to those theorems. So Jordan canonical form. Let P from V to V be a linear operator on a finite dimensional vector space V. Okay. Then, okay, sorry, finite dimensional vector space V. Then what I just wanted to say, let vector space B over a field, over an algebraically closed field. For example, you can consider it as a complex number. Why I am needing this? There is a purpose. Algebraically closed field. Example, F is equals to C. Okay. Let Fx, because if it is algebraically closed field, in that case, the characteristic polynomial is completely factorized into linear factors. Need not be distinct, but completely factorized. Even if the Jordan canonical form, or even the characteristic polynomial of a linear operator T is completely factorized in this way, the field is not algebraically closed, still these theorems will going to hold. There is no problem. My purpose is to get something like this for the characteristic polynomial, that x minus c1 to the power d1, x minus c2 to the power d2, x minus ck to the power dk, where c1, c2 all the way ck are distinct eigenvalue of t. Let mtx is equals to x minus, or px, whatever I'm using, px equals to x minus c1 to the power m1 all the way x minus ck to the power mk be the minimal polynomial. So the Jordan canonical form. So possible. So the Jordan canonical form of T with this. So there is no problem with the basis actually, because whatever the basis you may use Jordan canonical form will be same. There is no problem with the basis because matrix representation are similar, and Jordan canonical form is same for the two similar matrices. That's why it is not going to create any chaos. So Jordan canonical form of T will contain blocks, diagonal blocks. First block will be, if we have m1 here in the minimal polynomial, the first block will be c1 1 0 0 0, something like that, 0 c1 1 0, something like 0 0 0 c1 1. Suppose this is the last row, this is the last column, and this is the last row, 0 c1. So this is what I am just trying to say is that, and m by n upper triangular m by n upper triangular matrix whose diagonal contains Ci or C1 for M1 times. So basic, yes, yeah, right. Contains C1. So basically, other one will be similarly contains C1 and principal super diagonal. Super diagonal, yeah, and the what is called that principal super diagonal. Principal super diagonal. I hope I'm saying correctly. Principal super diagonal should be 1, or entries in principal super diagonal should be 1, and entries in the principal super diagonal is 1, and all other entries are 0. All other entries are 0. So this is a block. So what I just wanted to show, so Jordan canonical form of the matrix will be something like that. This is block, this is a block, this is a block, something like that, and all other entries are 0, something like that. This will come to this. So that means basically diagonals will be block, something like that. But what are the block? First of all, if you have a characteristic polynomial should look like this way, and minimal polynomial it look like this way, then there will be at least one block, which will be look like this way, corresponding to C1. I'm talking about only corresponding to C1. At least one block which will be look like this way, and all other block involving C1 will be of this form, but of order. So basically, all other blocks involving C1 should look like, should be in similar form of order some R1 times R1, where R1 should be less than equals to M1. So basically, what I'm saying, if you want to write, so basically if you want to write a Jordan canonical form for a matrix, for a linear operator T, which for which the characteristic polynomial and minimal polynomial, just I have mentioned like the way this is there. So what it will be? First, you have to write a block which will be look like this way, right? And then you have to first do the job for C1. And what is the job for C1? First you have to write the block corresponding to C1, at least one block of this form. Then the next block will be of same form, but the order here, order is M1 times M1. But the next block can be of order M1 or less than M1, but it can't be order more than M1, corresponding to C1. But the question is that how many such block will be appear corresponding to C1. This is one fact, this is second fact, and third fact is that corresponding to C1, the number of blocks is equal to the geometric multiplicity of C1. C1 is an eigenvalue because I have taken that field is algebraically closed or complex number. So in that case, the linear operator will always have eigenvalues the corresponding to specific eigenvalue C1. So what will be? First you have to give a block. Okay, that block will be of order M1 by M1 and which will be look like this way. In fact, any block which will be look like this way. Either that will be corresponding to C1 or corresponding to C2 or C3, that doesn't matter. Block will be look like this way. It is understandable that for the Ci it will be like Ci, something like that. So all the others will be Ci, something like that. But all other, I mean, at least one block of that M1 order, and there can be other block which is also of M1 order. But the number of block will be exactly equal to the geometric multiplicity, and the blocks will not be order of the blocks should not exceed this M1. Here is one fact. I mean, you have already, maybe you have read this, why this is happening. There is a very strong theory behind this, but I am not using this. Here is one fact I just want to point out, which may connect you to why this is happening. This is an interesting matrix. If you remove C1 from here, or for example, suppose this is a matrix A1, right? So now if we write A1 minus C1, or C1 identity minus A1, C1 identity of M1 by M1 order. Okay, so I hope you have, so C1, so here I just wanted to say C1 identity of M1 by M1 order and minus A. So what will be that matrix? That matrix will be the matrix where C1, all this matrix will be something like 0, 1, 0, 0, 0, 0, 1, 0, 0, all the way 0, 0, 1, something like this. This will be a matrix, upper triangular matrix, where all the entries are 0 and the principal super diagonal will contain 1. So that means there will be M1 minus 1 number of 1. I hope it is clear. Even it is not clear, because this is something very interesting patterns, so which will help you to remember why this is happening. Okay. So this matrix will be something like a matrix 0, 1, 0, 0, 0, 1, 0, 0, 0, something like this for the case M1 equals to 3, right? So now the most important fact is that if we take, this is the matrix that C1 minus A is equals to whatever it is, that matrix. If you take power m1, that will be 0. But if you take power less than m1, that need not be 0. In fact, that will not be 0, not need not be. That is a nilpotent and whose nilpotency is actually m1. If you take power something which is less than m1, then it is not going to be 0. In fact, you can check that specifically. If you take this is the matrix, suppose m1 is equals to 3. So in that case, this is something like, after removing c1, 0 0 1 0 0 1. So this is the matrix. If you take square, still this is going to be, this will be 0 0 1 0 0 0 0 0 0, and I hope I'm writing correctly, 0 0 1, that's correct, 0 0, that's correct. Now if you multiplied 0 1 0 0 0 1 0 0 0 and 0 0 1 0 0 0, then it will be 0 0 0, all the entries will be 0. But this is not 0, right? So, and why this pattern is there? Suppose you can deal Suppose you can deal all the eigenvalue case separately. Okay. Suppose you have the freedom to deal all the eigenvalue case separately. So in that case, characteristic polynomial is x minus c1 whole to the power d1, and the minimal polynomial is x minus c1 whole to the power m1. Right? Now, minimal polynomial, what is mean by minimal polynomial? Minimal polynomial is that polynomial such that mx mt is equals to 0, but no polynomial, no monic polynomial of less degree means degree less than m, is going to be 0. I mean, if we consider a polynomial whose degree is actually less than m, then that polynomial is not going to annihilate the linear operator t. So that's why if you replace at the place of xt, then suppose t is that Jordan canonical form. If you replace at the place of x that matrix A, the Jordan canonical form, then this is the polynomial and smallest degree monic polynomial which will make that matrix to 0. Right? I hope these facts are clear. So why? So that's why there will be at least one factor, one block corresponding to this m1 by m1 order. Because if you take block less order, then suppose here the block will be like 0 1 0 0. So this is going to be like 0 1 0 0 square is actually 0 0. So then why anyone will be bothered to take x minus c1 to the power 3? One should take the minimal polynomial should be x minus c1 to the power 2, right? My point is that suppose d1 is equals to 4, okay, and m1 is equals to 3, and you have only one eigenvalue. So then if you consider the matrix like 0, consider the c1 1 0 0 c1 1 0 0 c1, and this is 0, this is 0, this is just c1. Suppose this is the matrix, okay. So in that case, note that here C1 appears 4 times. So that is what it is, the D1 algebraic multiplicity, number of times each eigenvalue will appear. And M1 is actually 3. So that means this will be this. So for this matrix A minus C1, or basically A minus C1 times identity whole to the power 3 is 0. But A minus C1 to the power 2 is not equals to 0. But if we take, instead of this matrix, if we consider the matrix C1 1 0 0 C1, and another is C1 or these are all 0. These are of diagonal entries, C1 C2 are diagonal entries. This is matrix, or another matrix is something like C1 1 0 C1 C1 1 0 C1 C1 1 0 C1. So in each of the matrix, if you consider this is as A1 and this is as A2, then each of the matrix A1 minus C1i whole square is equals to 0. So that means for this matrix, minimal polynomial is is of degree 3, that is x minus c1 whole to the power 3. But for these two matrix, minimal polynomial is equal to x minus c1 whole to the power x minus c1 whole to the power 2, right? But both the for both the matrix, the characteristic polynomial is x minus c1 to the power 4. Okay. For both the situation, there is three matrix A, A1, A2. For all of the matrix, characteristic polynomial is x minus c1 to the power 4. That you can easily check. But for the first matrix, the minimal polynomial is x minus c1 to the power 3. For the second matrix is x minus c1 to the power 2. And for the third matrix is also x minus c1 to the power 2. So that means these two matrices have same characteristic polynomial, same minimal polynomial. But what is the difference here? If you look at carefully, here one block is of 2 by 2, that's clear. Other two block is, here is 1 by 1 block, here is 1 by 1 block. But in the second case, here is the 2 by 2 block. So if you remember, here I have said the number of blocks is actually same as the geometric multiplicity of C1. And geometric multiplicity is actually the number of eigenvectors corresponding to that eigenvalue. That means in this case, the eigenvectors corresponding to this eigenvalue is actually 3, because there is 3 blocks. This is first, this is second, this is third. In this case, the number of eigenvectors corresponding to the eigenvalue C1 is 2, because there is only 2 blocks. So as I have said, there is a very interesting and important, technical theorems behind this. But these are the things how connects you that why minimal polynomial. Minimal polynomial is something that the minimum power, right? Below that, it will not going to be 0. So here is the reason why this block has to appear. Why this block has to appear? Why the lesser block is not going to appear? Okay. What I'm here, first point I have said that there will be at least one block, and that is the first block of order m1 by m1, which should be look like this way. So I hope this is clear. So any doubt, at least till whatever I have said? Sorry. Any doubt till now, whatever I have said, like whatever I have tried to explain, or these are not proper theories, but rather it's some facts. So these facts are clear to you, or did you have any something doubt? So these are the facts. So let's get back to the problem. So if I need anything later that, like regarding this, then I'll mention. Okay. So whenever diagonalizable, then one fact here, whenever diagonalizable, that means the minimal polynomial will be x minus c1. So that means the largest factor that will be of c1. So all the factor will be c1. C1, there is no smaller factor than only this. So that means that in that case, linear operator will be diagonalizable. And what is the Jordan-Cannonical form is actually saying? The Jordan-Canonical form is saying that suppose you have a linear operator T from a vector space V to V, and we have a basis B, and we have a matrix T, representation with respect to that basis. Jordan-Canonical form, this corresponding to this linear operator, is actually that operator, the Jordan-Canonical form of the matrix T. Actually, that says that there exists an invertible matrix P, square matrix of order n by n, if dimension of V is n, such that P inverse TB P is actually JT, right? JT can be diagonal, JT can be non-diagonal. Diagonalizable, if you recall the diagonalizable definition, that says that there exists an invertible matrix P of order n by n, such that P inverse TBP is a diagonal matrix. But if it is not diagonalizable, then this is the Jordan-Canonical form is the best purpose of diagonalizable. Is that suppose you have a matrix T or linear operator T whose matrix is B, that can be something very involved, right? Some term is here, some term is here, some term is something like that. But diagonal is that okay? That is similar to a very simple form of matrix. Diagonal matrix is very simple form. Now, if it is not diagonalizable, then then this is what it is happens. The Jordan-Canonical form, that is the simplest form. Jordan canonical form is the simplest form. Jordan canonical form is the simplest form. Okay, sorry. Jordan canonical form is actually the simplest form, which is actually analogous of diagonalizability. Okay, now let's get back to the problem. I know today maybe not much problem will be solved, but I'll try to give as much information as possible. Okay, so I hope problem is clear, visible to you. So let V be the vector space of over R with the dimension 10 and T be a linear operator on V. Let the minimal polynomial, so minimal polynomial for P is a minimal polynomial. Okay, this is not characteristic polynomial. Minimal polynomial for P is actually x plus 1 to the power 5, x minus 3, and x plus 11. Okay, so that says the eigenvalues are minus 1, 3, minus 11. Okay, and if you look at carefully, for x minus 3 there is 1 power, and x plus 1 there is 1 power. So that means all the factor corresponding to that will be single factor, but for x minus 1 that will be 5, at least there will be one 5 by 5 factor, right? And the, oh sorry, here I have written little wrong. Minimal polynomial is this. So no, so that means you have to factor it more. So this will be like x plus 1, x minus square root of 3, x plus square root of 3. Yeah, this is correct. And x plus 1. This is the minimal polynomial. So eigenvalues are minus 1, square root of 3, minus square root of 3, oh, minus 11. So, and if you look at carefully that x minus 3, there will be at least one block of order 1. X plus 3, there will be of one block of order 1. Corresponding to 11, there will be one block of order 1. That means there will be 3 diagonal entries are fixed. Now corresponding to x plus 1, 5, there will be at least one block of order 5. So that means 5 diagonal entries are fixed. So now let's see what we have. That V with the vector space of R of dimension 10 and T with the linear operator on V. Let the minimal polynomial of T is this. Let the geometric multiplicity, here it is written that geometric multiplicity of root 3 is actually 2 and geometric multiplicity of 11 is actually 2. So now, what is the Jordan form? First of all, one block will be like minus 1, 1, 0, 0. I need the 5 by 5 block. 0, minus 1, 1, 0, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, 1. Oh, sorry, minus 1. This is the, I'm written correctly. So this is corresponding to x plus 1, 5. And you have minus 3 square root of 3, so that is square root of 3, this is corresponding to square root of 3, minus square root of 3, this is corresponding to minus square root of 3, and and actually for square root of minus 3, sorry, square root of 3 there is 2 block, so square root of 3 at least that will be root 3, 0, 0, root 3 for root 3, as geometric multiplicity of root 3 is actually 2, and corresponding to 11, minus 11, there will be at least 2 block minus 11 for lambda equals to minus 11, as geometric multiplicity of minus 11 is 2. And what are the other left? This is a 10 dimensional V, dimension of V is actually 10. So here, so matrix will be 10 by 10. So here 5 gone, here 2 gone, here 2 gone, so 9 is already gone. So there is only one factor, that is minus root 3 for lambda is equals to minus root 3. So, Jordan canonical form will be, if I write this is A1, this is A2, this is A3, this is A4. So the matrix Jordan canonical form is actually A1, A2, A3, A4, and all other entries are 0. So, so is it clear why this is Jordan canonical form? If you have doubt, you can ask, because this is very important topic. It's better to repeat. Not that there is no problem, no harm to repeating this, because this is very important topic, and most of the, I mean, fundamental target of the basic linear algebra is to reach up to Jordan canonical form. Okay, so if you have doubt, you can. I mean, you should not hesitate to ask here. So, because this is very important to me, as I have said. So as geometric multiplicity of root 3 is 2, so therefore there will be 2 block of root 3. So this is the 2 block of root 3, and corresponding to minus root 3 there will be 1 block, and corresponding to minus 11 there will be 2 block, and corresponding to minus 1 there will be 5 by, there will be a 1 5 by 5 block. So this is the option. So all other options are incorrect because there is no other possible choice. Suppose you are giving two geometric, suppose you are giving all this fact, I mean there can be something where all the information here, what are the information given? Information given geometric multiplicity, sorry, minimal polynomial, information given geometric multiplicity of two vector, not the all of them. Still we are able to get exact the Jordan canonical form. Sometimes it happens that we are giving characteristic polynomial, minimal polynomial, and geometric multiplicity corresponding to some facts. In fact, geometric multiplicity corresponding to fixed linear operator. Still, you will not be able to. For example, what I just wanted to say is that sometimes geometric multiplicity is also not able to help you to exactly find a single Jordan canonical form. For example, suppose I am getting the, let me write, suppose this is the minimal polynomial. So let me write this is 3. This is something like home, so something like exercise you can say. This is also exercise. Let be the minimal polynomial and characteristic polynomial is some power which I am going to replace, but according to our demand. Let's take geometric multiplicity of C is actually 3, and that means there will be 3 block. So that means D1 can be maximum 9. There is no other choice because 3 block and maximum block is actually of order 3. So C1 0 C1 0 0 0 C. This is the first block. Geometric multiplicity is 3. But suppose I wanted to write it as geometric multiplicity, write it as 4. Yeah. So suppose another block is 0 1 0. See, this is another block. Another block is C1 0 C. This is another block. Another block is C. Right. This is a possible Jordan canonical form. Geometric multiplicity is 4, and minimal polynomial is x minus, and here 3 3 5, and D1 is actually here 4 5 5 3 8. D1 is 8. Okay, so that's clear. What are the other option? One option will be that there is no doubt. Other option is that we can also choose 6 is gone, C is C. There is also 8. Here is also Jordan canonical. Here is also the minimal. I mean, minimal polynomial, characteristic polynomial, geometric multiplicity. All the facts for these two matrices are same. That is what I wanted to say. Okay, so geometric multiplicity of C is actually 4. Algebraic multiplicity is actually 8. Minimal polynomial. So minimal polynomial is x minus c to the power 3, and characteristic polynomial is x minus c to the power 8. So all the facts are same. Still, there is a two possible form of Jordan canonical matrix. Okay, so that means, but these two matrices are not similar. So if I write this is as A1 and this is as A2, A1 and A2 are not similar. A1 and A2 are not similar. So what we obtain here, even if you are said that okay, suppose you have been asked somewhere that you are giving minimal polynomial, characteristic polynomial of a linear operator, and geometric multiplicity corresponding to each eigenvalue, whether the Jordan canonical form is unique or not. The answer is no. Jordan canonical form need not be unique. There is two possible here for example in this case two possible options is there. Okay. So sometimes it feels that if you are given a matrix and where Jordan canonical characteristic polynomial, minimal polynomial, geometric multiplicity, everything is same, that then sometimes feels that okay Jordan canonical form may be same, but that's not necessary. But if you are considering a Jordan canonical form, then in that case the characteristic polynomial, minimal polynomial, geometric multiplicity all has to be fixed. You can't change that. Okay. Okay, so I hope this fact is clear. So let's go to the next problem. Sometimes questions will be asked. I mean, nowadays the questions are in mostly competitive exams. They will not ask you to give you the Jordan canonical form because those days already gone. Right now they ask you some questions from where you have to answer that questions or the answer for that questions will be easy if you try to find the Jordan canonical form. From the appearance, mere appearance of the questions, you will not be able to understand whether you need whether you need to go to the Jordan canonical form or not. But if you are going to Jordan canonical form, if you are smart enough to go to the Jordan canonical form or guess enough that if you are smart enough to guess that Jordan canonical form is the way, then you can answer those questions. Okay, so let's get back to this problem. So what this problem says, let T from R4 to R4 be a linear operator such that rank of 2 is equals to 2. Rank of T is equals to 2. In which of the following statement is or are correct? T is diagonalizable, nilpotent. T is diagonalizable, then it cannot be nilpotent. T is nilpotent, then it cannot be diagonalizable, and T is always invertible. First of all, if rank of T is equals to 2, then so let T be the matrix of T, matrix representation of T with respect to the standard order basis. Okay, this is a matrix. I am not going to the matrix actually. Here it is not given anything else. So rank of T is 2. That means that says as rank of T is 2, that says two facts. First fact is that T is not 0. That is T matrix B is not 0 or not nilpotent or not no, nilpotent can be sorry nilpotent can be. And second fact is that determinant of T is actually 0 because if determinant T is non-zero, then determinant of TB is actually 0, T not T. Determinant of TB is actually 0 because if determinant of TB is non-zero, two fact, TB is not a zero matrix, but determinant is 0. This is what it is I wanted to say. Because rank is 2. Because if it is zero matrix, then it will be similar to if it is zero matrix, then there will not be any non-zero row, right? At least there will be an existent basis. If it is zero matrix, that means there should exist a basis for which there will not be any non-zero row. So okay, but that's not the case because rank is 2. There will be two non-zero row. Another fact is that as rank 2 is 2 and here T is a linear operator on dimension 4, that means the matrix representation of T with respect to any basis will be 4 by 4 matrix. That means T is not invertible because if it is T invertible, then rank will be 4. That's clear. So that's why it is 0. So that means uh, if it is nilpotent, for example, if it is nilpotent, then if T is nilpotent, then characteristic polynomial should be x to the power 4 is equals to 0. Characteristic polynomial should be. 0. But as TB is not identically 0, that implies the minimal polynomial will be x to the power k, where k is actually strictly greater than 1, because k can't be 1. Because if k is 1, that means the TB is equals to 0. Minimal polynomial is that, no, right? That MT is equals to 0. Okay. And k will be less than equals to 4. That means the minimal polynomial can be, in this case, x square, x cube, or x4. Okay. But as the minimal polynomial is not product of, only possible, these are the only possible choice. X square, x cube, x to the power 4. But note that in each cases, note that in each case, T is not diagonalizable, because if T is diagonalizable, then its minimal polynomial has to be distinct linear factors. But here x square, x cube, x3, they are not distinct. X dot x, they are not distinct. X cube is x dot x dot x, they are not distinct. That means what we obtain, these are the simple facts that we got. That the linear operator T is not diagonalizable. Sorry, if it is nilpotent, then it is not diagonalizable. This is what it is. So one option will be discarded, I think. T is nilpotent, then it cannot be diagonalizable. This is the first fact is true. This is the one correct statement. Second fact is that T is diagonalizable and nilpotent, and that can't happen simultaneously. That we got. That means this option is also incorrect. That T is diagonalizable and nilpotent can't happen, right? Because if it is nilpotent, then x to the power 4 is equals to 0 is the quadratic polynomial. Then minimal polynomial has to be x equals to 0. But this information says that the minimal matrix is a non-zero matrix. What is second information says? If T is diagonalizable, then it can't be nilpotent. That's also true. T is not invertible, that is also clear, because determinant of T be 0. This is also clear. This is not true. So what the second option says, if T is diagonalizable, then it cannot be nilpotent. If it is nilpotent, the same fact, if T is diagonalizable, then minimal polynomial for option 2. If T is diagonalizable, then if characteristics polynomial the minimal polynomial, then its minimal polynomial should be of the form x minus c1 to the power k, x minus c1, x minus c2, x minus, basically x minus all the way dot. I have to write something like this way. Ck for k equals to 1, 2, 3, for any of the option. Okay, because that has to be distinct linear factors, and c1, c2, ck are the distinct. But in that case, T is not diagonalizable. So then D is not nilpotent. In any case, what are the options? This option T is diagonalizable, then it cannot be nilpotent. It can't be nilpotent. That's clear, na? T is diagonalizable. If T is diagonalizable, then it will be look like this way. Minimal polynomial will be look like this way. Okay. So then, what are the least choice? And if it is nilpotent in addition, if it is nilpotent, then minimal polynomial is x, but that is not the case. That can't happen. So that's why this third option is also incorrect. Is it clear? If you have any doubt, this one you can ask. Even if you have any very simple doubt on why this, I mean, some argumental or anything, you can ask. I'll try to explain those things. Oh, sorry. This is the correct option. T is diagonalizable, then it cannot be nilpotent. That is what we are proving, right? T can't be nilpotent. So that is what we have proved. In addition, if T is nilpotent, that can't happen. That means T can't be nilpotent. This option is also correct. Main point is that T is diagonalizable, then it can't be nilpotent. Okay, so what are the some this type of example? This example is something like 0 1 0 0 0 0 1. This is the rank 2 0 0 0 0 0 0 0 0. So look at carefully. This is a rank 2 matrix because there is two non-zero row. Determinant is 0. That's clear. Because if determinant is non-zero, then it will be invertible. Invertible means range will be dimension will be 4. So that means that will be. So I hope it is clear. I'm going to next problem. So what this problem says, let B be a 4 by 4 matrix over C with rank of B is equals to 2 satisfying B3 is equals to B square. So that means the minimal polynomial, so the matrix B satisfies the polynomial equation x cube minus x square is equals to 0. That means x into x minus 1 x square is equals to 0. This is what it is. And but b square is not equals to 0, right? That means that is the minimal polynomial. So what are the possible choices of minimal polynomial? Polynomial for B is either x or x square or x into x minus 1 or x minus 1 or x square x minus 1. These are the five choices. But here it says that b square is not equals to 0. That means this is not the option. But if b square is not equals to 0, then b can't be 0. So this is also not an option. So these are the four options left. Three options left. Okay. And b is not diagonalizable. B is not diagonalizable. That says this is also not options. Okay. So let me, as b square is not equals to 0, then minimal polynomial cannot be x or x square. As b is not diagonalizable, as b is then minimal polynomial cannot be x minus 1 or x minus 1, because in each of the cases minimal polynomial is actually the product of distinct linear factors. So that's why by that theorem that T will be diagonalizable if and only if its minimal polynomial is product of distinct factors. So that's why it is said that T is not diagonalizable. So that's why these are done. So the only option left, only choice left for minimal polynomial is x square x minus 1. Okay, this is the minimal polynomial. Okay. Now let's come to the question. Then which of the following option is or are correct? one of the Jordan blocks. Here it is matrix of 4 by 4. Okay. So then as B is 4 by 4 matrix, then options choices for characteristics polynomial are, there is two choice. One is x square x minus 1 square, another is x cube x minus 1, because minimal polynomial should divide the characteristic polynomial. So that means you can increase, you can go to 4 from here, 4-degree polynomial by either at right increasing power x or increasing power x minus 1. These are the options. Now, so if you have minimal polynomial look like this way, now the Jordan canonical form in the setting x square, in the setting minimal polynomial is actually x square x minus 1 and characteristic polynomial is actually x square x minus 1 square. In this case, corresponding to 0, there is a 2 power. So there will be 1 0 by 1 2 by 2 block, and this is the 0 corresponding to 0. Now corresponding to 1, there will be 1 block and 1 block, because minimal polynomial power is 1. So as minimal polynomial power is 1, so that means the largest block corresponding to 1 will be 1 by 1. And as the characteristic polynomial has power 2, so to fill that I have to go down. So but there is only one option. I can choose only one block, 1 by 1 block corresponding to 1. So is the Jordan canonical form. In the setting of minimal polynomial is actually equals to x square x minus 1 and characteristic polynomial is this is characteristic polynomial x cube x minus 1. So here is, as the minimal polynomial corresponding to x 0 is 2 power, so therefore one block will be this one. But here the characteristic polynomial has power 3. So that means I have to go down one. Just 1 minute, I will be back. Sorry for the. Yeah, sorry for the inconvenience. So okay, so one block will be of degree 2. So what are the other block? So we have to fill 3 corresponding to 0 eigenvalue, right? So here is one more block. So what is the, I mean, that can be of 2 order or 1 order, but this is what it is, the other order, because there is, I have to fill 3 and corresponding to 1 there will be 1. So these are the Jordan canonical form. Is So let me go back to the options. So one of the Jordan blocks of the Jordan canonical form B is 0 1 0. That has to be appear. That's clear, because that appears in each of the time. This is also there and this is also there. And second option is that one of the Jordan block of the Jordan canonical form is this. That can't happen, because we have to check all the options. And I don't understand why this is. This is the I don't understand what this third option says. Third option is automatically correct, but this is what it is giving. I'm just trying to. A is true. I have to find the answer. Option is b square equals to b or not. Sorry, I'm reading incorrectly. B square equals to b or not. Whether this is possible or not. Because if b square is equals to b, then the minimal polynomial should be x square is equals to x. That means x into x minus 1, right? This is the minimal polynomial. Minimal polynomial, but that can't happen because t is not diagonalizable. That we already discussed, but again I am discussing. Another fact is that there exists a vector v not equals to 0 such that bv is equals to not equals to 0 and b2v is equals to 0. This is very interesting option and this is correct. But why this is correct, that I am going to, I already discussed somewhere. But so if you go to back to the due to for option 4, for option 4. What is the option D I am writing? What is the statement says? There exists a vector v not equals to 0. There exists a vector v not equals to 0 such that bv not equals to 0 but b square v is equals to 0. I hope I have written correctly. Yeah. So note that here characteristics, sorry, minimal polynomial is x square x minus 1, right? So there is two irreducible. This is p1x square p2x, where p1x is equals to x and p2x is equals to x minus 1, right? p1 and p2x equals to. Now due to primary decomposition theorem, primary decomposition theorem, if W1 is equals to dimension, uh, W1 is equals to kernel of T1 square, that is P1 T square, P1 is X, this is P1 is X, then, so the X is the eigenvalue, right? So corresponding to that eigenvalue, the algebraic multiplicity is actually 2 or 3, whatever it is, right? But at least algebraic multiplicity will be 2 because the minimal multiplicity is 2. That's why then corresponding to then dimension of W1 at least greater than equals to 2. Why? Because if you remember that W1, dimension of W1 is actually the number algebraic multiplicity corresponding to that eigenvalue. Now, as the minimal polynomial, in the minimal polynomial, the degree of x is 2, then algebraic multiplicity, in the algebraic multiplicity also it will be at least 2. The dimension of W1 is equals to 2. And if you remember carefully, once I was trying to say that kernel of t minus, for this type of situation, kernel of t1 should be, or kernel of t minus 0, here it is 0 dot I, this is a subspace of kernel of t minus 0 dot I square, and after that it will be neutralized. Okay, so my point is that clearly kernel of t minus I does not have dimension 2, because no, that can have dimension 2. No, dimension can't be 2. Sorry, just a minute. Here it will have, here of course we will have, but here is the, I mean, this last option will be correct. That is what I am trying to say. I want to trying to say that this is proper containment. This containment is proper. If this containment is proper, then there will exist a vector such that t square v is equals to 0, v is non-zero, but tv is not equals to 0. This is what it is, right? This is what I am trying to say. But how I can say here? There will always exist some vector. Okay. If characteristic polynomial is x square, or this is not equals to 0 if, so note that. Just a minute. No, in each cases it will be right. I don't need to go separately. This is what it is. This is what it is. Because if character is okay, okay. So let me give you the reasoning for this proper method. Because this properness, this happens because as dimension of W1 is actually greater than equals to 2, and if kernel of T is actually dimension, dimension greater than 2. So if characteristic polynomial is x cubed x minus 1, then this dimension is actually 3, right? Then if dimension of kernel of T minus I is actually 3, then T should be diagonalizable, but this is not the case. But this is not the case. Okay, I want to make it more elegant. So if you go to the primary decomposition theorem, what it says, the kernel of P1T by primary decomposition theorem, PMT, primary decomposition theorem, by primary decomposition theorem, if W1 is equals to dimension of P1T square and W2 is equals to dimension of P2T, then V is actually direct sum of W1 plus W2. Here V is 4-dimensional space. WT algebraic multiplicity is this. Sorry, geometric power in the minimal polynomial is this, and the power in the characteristic polynomial is also this. So that means here we have only one eigenvector corresponding to x equals to 1. But then W1 space is actually, in that case, W2 is actually the eigenspace, right? So that means that W1 should have the dimension 3. Now, now primary decomposition theorem, the dimension of W1 equals to 3, which is actually dimension of T minus 0 dot I3, right? Now, if kernel of T minus I is actually, this is what it is 2, sorry, 2, huh? If kernel of T minus I is 3 actually, then what it is means that W1 is actually, I mean, in that case, still be diagonalizable, but that's not the case. So that means kernel of T minus I is actually not 3. That will be less than 3. Okay? Because otherwise, we don't need this fact, right? That is, there exists a vector v not equals to 0 such that T minus Tv is equals to not v, because that is not in the kernel. That is what I wanted to say. But T square v, so T square v not equals to 0, T square v is equals to 0. If characteristic, this is all for characteristic polynomial, this one, x cube minus x. Characteristic polynomial is x cube x minus 1 square, right? Then W1, those are as it is. Then dimension of W1 is actually 2, because here many facts is there actually. W1, this will be true, but dimension of kernel 0i, this will be less than 2. That's why we need the second power, right? That means there exists a vector v not equals to 0 in the space vector space v, such that tv is not equals to um, tv is tv is not equals to 0, but t square v is equals to 0. Okay. Primary decomposition, if I just want to say what primary decomposition trying to say, then this will be clear. Primary decomposition, suppose you have factor x1 minus m1 and x minus c2 whole to the power m2. This is the minimal polynomial. And the Cash-Static polynomial, or suppose consider it is one power, okay, only one power. Now 2 is needed, x minus c2 whole to the power m2, okay. Now suppose this is the suppose minimal polynomial. And suppose the minimal, so this is the minimal polynomial. Cash-Static polynomial is actually x minus c1 whole to the power d1, x minus, I have written 2 only, x minus c2 whole to the power d2. So the primary decomposition theorem says that if t minus c1 kernel of t minus c1 to the power m1 is equals to w1, and the kernel of t minus c2 to the power m2 is equals to w2, then v is actually w1 direct sum w2. This is what it is, first fact. Now that means if you take lower kernel, basically from here, just from here, you don't need to do anything. That means kernel of t minus c1 to the power some m1 minus 1, that will be proper subspace, that will be exactly proper subspace of kernel of t minus c1 minus c1 to the power 1. You can remember this, and then that theorem will be very much easy, because in that case, in the previous case, the x square is appears. So as x square appears, kernel of t minus c1, that is 0 dot I, this one will be proper subspace of kernel of t minus c1 m1. This is a fact. We can remember this as a fact. So then it will be done. I mean, I need to mention some theories here. There is a background theory, but I don't want to. I don't want to mention why that background theory came here. So this is one, the fact that primary decomposition theorem that kernel of t minus c1 to the power m1 minus 1 is proper subspace of kernel of t minus c1 minus. But after that, kernel of t minus c1 to the power some any k, where k is greater than equals to m1, that will be same. Okay. So I hope it is clear. If you remember, if you recall this fact, then I hope this will be clear. So that means the last fact is correct. First and last option is correct. Is it clear? I hope there is some new terminologies, but if you just remember this one, this will be clear. I mean, something like that. What is the layman language terminology is that? Yeah. So, but layman language terminology is that suppose you have diagonalizable operator. That means kernel of t minus c1 that is enough. But if you don't have diagonalizable, then this is not enough. I mean, this type of space, these kernels. I mean, suppose you have c1, c2, ck are eigenvalue. Okay, and you are considering kernel of t minus c1 I. And T is diagonalizable means if you take collection of all those kernel, that will fill the vector space V. Basically, that will form a basis for the vector space V. That is what it is mean by diagonalizability. But if it is not diagonalizable, then those kernel does not fill to form a basis for the vector space V. But to get the some linearly independent set or basis, we will be considering the lowest power of t minus c1 I, right? So basically, if this is in general too. Suppose this is in general too. This is very in general too. C any vector. C is not any vector. In fact, C is any element in Phi. Then kernel of t minus ci. This is contained in kernel of t minus ci square. This is true. So whenever you have diagonalizable, in that case, if c1, c2, ck are the distinct eigenvalue, then t minus c1 I kernel of t minus c1 I, if I take union of all I equals to 1 to k, that will span the vector space V. That is what it is mean by diagonalizability. But if it is not diagonalizable, then this is not enough to fill the vector space V. But that will be a proper subspace of the vector space V. To get, so that means some vectors will be missed to form a basis. So to get the desired vector space, we have to go at least a little power, till to little power of the t minus ci to the power, right? So to that little power is actually the power of the x minus ci in the minimal polynomial, right? So there is very interesting connection. I mean, I hope you will be it will be clear to you someday. Okay, so let me do this, and I hope this will be the last problem. Okay, so this is another problem. So let's do this quickly. Okay, so what it says, let A be a matrix 3, 1, 0, 0, 3, 2, 4, something like this. So corresponding to this matrix, characteristics polynomial is clearly x minus 3 square, x minus 4. And for this, so what are the possible choice of minimal polynomial? X minus 3, x minus 4, or x minus 3 square, x minus 4. So let's check whether this is satisfying or not. So a minus 3i means a minus 3i, a minus 4i, which is equals to 3i means 0, 1, 0, 0, 0, 2, 0, 0, 1. This is 3 minus 1. 4 minus 1 means if I subtract 4, so what it will be? It will be minus 1, 1, 0, 0, minus 1, 2, 0, 0, 0. So if you multiply, this will be first term will be 0, second term will be minus 1, third term will be 2, and so this is not becoming whatever it is, that is not 0. So characteristics polynomial, so minimal polynomial, that is I think written A, minimal polynomial of A is actually x minus 3 square x minus 4, right? Now minimal polynomial, sorry, characteristics polynomial for the matrix B, which is actually given like diagonal 3, 3, 3, 0, 0, 3, 0, 0, 0, 4 is x minus 3 square x minus 4, and this is diagonalizable, that's clear. This is diagonal matrix, and minimal polynomial is x minus 3 x minus 4. So we have two matrices. One is A 3, 1, 0, 0, 3, 2, 0, 0, 4. This is one matrix. Another is B, that is 3, 0, 0, 0, 3, 0, 0, 0, 4. So in this case, characteristics polynomial is x minus 3 square x minus 4. Minimal polynomial is x minus, this is same with the characteristics polynomial. In this case, characteristics polynomial is x minus 3 square x minus 4, and minimal polynomial is x minus 3 x minus 4. So let's get back to the options. A, B are not similar over the field of real numbers. That's true. That's true. A, B are not similar, because if two matrices are similar, they should have same Jordan-Cannonical form. Similar means what? Similar means that there exists an invertible matrix P such that A inverse P BP, right? Suppose A is the matrix. Suppose A has Jordan-Cannonical form JA. So that means JA should be equals to Q inverse AQ for some Q, right? And if B is something like this, so that means if you replace this Q inverse A, sorry, if you replace here Q J A Q, suppose A is similar to B, that means we have this one for some invertible matrix P. Suppose the Jordan-Cannonical form for the matrix A is JA, that means there exists an invertible matrix Q such that JA equals to Q inverse AQ, right? This is what it is. Now Q inverse JAQ is equals to P inverse BP. So that means JA is equals to QP inverse BPQ. So that means there exists an invertible matrix QP inverse such that QP inverse BQP is equals to J. So let me write this one as a formally. For option A, if two matrices A, B are similar, they should have same Jordan canonical form. In fact, this is if and only. If you have same Jordan canonical form, they must be similar. Why? If A is similar, A is similar to B, that is, there exists an invertible P matrix, invertible n by n matrix P such that A is equals to P inverse B, sorry, BP. Now, if JA be the Jordan canonical form, then A be the Jordan canonical form, then there exists an invertible matrix, and there exists an n by n invertible matrix, n by n invertible matrix Q such that JA is equals to Q inverse AQ. That implies that JA Q inverse is equals to P inverse BP. That implies JA is equals to Q inverse P inverse B PQ inverse. That implies B should have the same Jordan canonical form as A has. Jordan canonical form as A has. So that means they should have same Jordan canonical form. So this is a short theorem basically. Okay, short lemma. But here in this case, what is the Jordan canonical form? Jordan canonical form is 31303. Actually, this is written in Jordan canonical form 004. This is the Jordan canonical form because the minimal polynomial has highest degree 2. Right. So that means there should be one block corresponding to 2, corresponding to 2 by 2 block corresponding to 3, and corresponding to 4 one block. And here Jordan canonical form is this is 300030004. This is diagonal, basically same. Jordan canonical same. So they are not have same Jordan canonical form. As A and B in this question in this problem is not same. A and B are not similar. A and B are not similar over the field real numbers. That first. A is diagonalizable over the field of real numbers. That's false because B is diagonalizable. B is the Jordan canonical form of A. That's also false. The characteristics and minimal polynomial of A are not same, but the characteristics polynomial and minimal polynomial of A are same. So that is also false. Is it clear? This why these options are A and B are not similar. That's clear, I hope, because they don't have the same Jordan canonical form. A is diagonalizable. That is also not clear because corresponding to A, the Jordan canonical form is actually minimal polynomial is x minus 3 square and x minus 4. From here you can say they are not diagonalizable. B Jordan canonical form, however, that is also not true because B is diagonalizable and A is not diagonalizable, so that's why they are not equal. And the characteristics and minimal polynomial of A are same. That's not true because the characteristics and minimal polynomial are not same. It is just not same, but the characteristics and minimal polynomial of A are same, and that is this. Is it clear? Okay. If you have any doubt, you can ask. Otherwise, I'll be assuming that it is clear. And this is, I think, this is not much involved, but one important theorem is that if two matrices are similar, they should have same Jordan canonical form. I hope it is clear. If you have any doubt, you can ask. Otherwise, I will stop in few minutes. If it is not clear, you can ask. I will try to explain because this is very easy questions. This will be very easy to understand, not difficult. So if we explain, then still it will be clear. Is it okay? So I will close the class in next one couple of minutes, 1 or 2 minutes. So I hope it is clear. So I will stop here. Yeah.